Hello everyone, my name is Escobedo and I'm pleased to present this work titled on the synthesis and phase constitution of bulk ulmium diborite-based alloys for hydrogen magnetocaloric liquefaction. On the occasion of the International Materials Research Congress 2025, in this project we synthesize and characterize 3 ulmium diborite-based alloys, 2 with the ulmium diborite composition, one in pellet form and the other in rod form, and a third with the composition you see here on the screen, in pellet form. One of the highlights of this study is the synthesis of a rod-shaped ulmium diborite alloy using the suction casting technique, which enables us to produce geometries that are more suitable for device applications. As many of you may know, hydrogen is a clean fuel with enormous potential. However, storing and transporting it in its gaseous form remains a major challenge. Liquefaction, which makes hydrogen nearly 100 times denser, is a promising solution. The challenge is that this process requires very low temperatures, and the efficiency of current liquefaction technologies is still limited. Magnetic refrigeration has emerged as an attractive alternative because it relies on the magnetocaloric effect, avoiding the use of harmful refrigerants and potentially offering higher efficiency. The key is to design materials with strong magnetocaloric responses, close to 20 Kelvin, which is the liquefaction point of hydrogen. Among the candidate materials, rare earth intermetallic alloys stand out, and in particular, ulmium diborite has been considered a benchmark material because it exhibits a large magnetic entropy variation and adiabatic temperature variation at the right temperature window. However, to implement these alloys in real devices, they must be fabricated in specific geometries, such as rods, to improve the heat transfer and integration into magnetic regenerator beds. To address this, we synthesize our alloys using 2 approaches. The pellet-shaped alloys were obtained by conventional arc melting, while the rod-shaped ulmium diborite sample was produced using the suction casting option. This technique is essentially a rapid solidification process. Once the pre-alloyed ingot is melted by arc melting, it is quickly drawn into a water-cooled copper mold by pressure difference, resulting in a cylindrical bar. This is important because it demonstrates the feasibility of fabricating device-ready geometries. Structural characterization was performed through powder X-ray diffraction and radial refinement using the foolproof suite. Microstructural analysis was carried out using scanning electron microscopy. Finally, we characterized the magnetocaloric properties by taking both magnetization and specific heat measurements, allowing us to estimate the magnetic entropy variation and the adiabatic temperature variation. Starting with the structural results, as we can see in Figure 1, X-ray diffraction confirmed that ulmium diborite is the main phase in all samples, with ulmium tetraborite detected as a secondary phase. In the case of the suction cast rod, small amounts of ulmium oxides were also identified. And here in Table 1, we see that the lattice parameters obtained are in good agreement with those reported in the literature. Additionally, we see that here the phase composition of each alloy. Now, here in Figure 2, we present backscattered SEM micrographs at different magnifications for all the alloys. In Figure A, we observe the typical microstructure of the as-cast ulmium diborite pellet, while in B, we see regions that show a preferential grain orientation in the solidification direction. In Figure C, we see a cross-sectional view of ulmium diborite rod-shaped alloy, revealing a cavity running through the sample due to the nature of the synthesis process. In D, we see a close-up view that shows grain boundaries that are oriented radially towards the center of the rod. And in in E and F, we see the typical microstructure of the ulmium gadolinium boron pellet. Consistent with the X-ray diffraction results, a significant two-tone contrast is observed in all the micrographs. The lighter regions correspond to the ulmium diborite phase, while the darker areas correspond to the ulmium tetraborite phase. The temperature-dependent magnetization curves for applied magnetic fields of 5 millitesla and 5 tesla are shown in figure 3 for all the alloys. The Curie temperature in each case was estimated from the derivative of magnetization with respect to temperature at 5 millitesla, as we can see in the insets of each figure. No clear evidence of a kink or a shoulder at the nil temperatures of the secondary phases was observed in the 5 millitesla curves, which is consistent with the low content of these phases. Furthermore, for an applied field of 5 tesla, we see a high saturation magnetization in each case. Finally, regarding the magnetocaloric effect, for the ulmium diboride alloys, for a 5 tesla field variation, we reach values for the magnetic entropy variation of approximately 40 joule per kilogram Kelvin and an adiabatic temperature variation of 12 Kelvin. In contrast, for the ulmium gadolinium boron alloy, we got values of 28 joule kilogram Kelvin and 11 Kelvin for the same field variation, but it has a broader transition. Interestingly, for a 2 tesla field change, the ulmium gadolinium boron alloy exhibits a nearly a table curve-like curve between the 12 and 24 Kelvin, and the Curie temperature shifts to 25 Kelvin approximately. These values are comparable to those obtained by other authors for the same alloys. Now, in Table 2, we summarize the magnetocaloric properties of the alloys studied in this work and compare them with data reported by other authors. To conclude, ulmium diboride retains excellent magnetocaloric performance when fabricated in device-ready rod geometries using the suction casting technique. Gadolinium substitution enables tuning of the operating temperature range while maintaining a high performance. Our results confirm the strong potential of ulmium diboride-based alloys for hydrogen liquefaction technologies. These results suggest that ulmium diboride-based alloys, particularly in rod-shaped form, are promising candidates for magnetic refrigeration devices aimed at hydrogen liquefaction. Thank you for your attention, and I will be happy to take any questions. Bye.